Okay, let's try to recap the last results I presented last week. Can you see everything? Is that okay? Oh, by the way, I uploaded both. I uploaded to the Virtuale both a kind of detailed syllabus with precise references to the chapters and sections in the main textbook, and a PDF file with a list of exercises. I mean, they are kind of minimum set of exercises. There may be more exercises that you can do with no difficulties, but they are, what is important is that they are similar, both in spirit and in the level of difficulty, to those solved here in the class, okay? So there is also a list of exercises, and there is also a text file with the links to all the videos of the classes. I'm not a specialist of that. I guess that you have access if you just click on these links and put your email as the access word or password. Is that true? I mean, can you access these links?
Lesson?
Did you try?
I've tried and I could do it, so for me it's fine.
Thanks so much for your feedback, because I see from the structure of the address, the URL, that it's very complicated. It's a kind of key, okay? So I suppose that if I obtain this link and I share it with you, you just must be enrolled to the University of Bologna, and that should work. So I'm happy. They're already there. I thought that they would have expired in about 1 month, but maybe 1 month is not over yet, or maybe they last longer. So let's hope the best. The videos are there. Okay, so this is I'm trying to recap the basics of the implicit function theorem to present you 2 examples plus 1. 2 examples in which we need the implicit function form of a function, because otherwise we cannot work out the derivative. And another example, which is very common, in which we could, in principle, solve the implicit function and compute the derivative directly, but it's more convenient to rely on the implicit function formula. Okay? So I'm going to present this, and next I will apply immediately the implicit function theorem and the implicit function derivative to the basic model of constrained optimization. Okay? So the framework or assumptions for the implicit function theorem are here. If you are interested in the theoretical aspect of this, you're welcome. Just go to the textbook and try to understand more, but I just want to interpret the main points, the main assumptions, okay? So we have an equation, f of xy equal to 0, or f of xy equal to c. Remember that this form is perfectly equivalent to this one, okay? So we could just move this to the left. We would have g of xy equal to 0, where g is f minus c. By the way, what we do here is computing the derivatives of f. We don't worry about the c on the right-hand side, okay? So this form is equivalent to this one. This is a general mathematical form, and this is the form that we get when we interpret an implicit function as a level curve of a 2-variable function, okay? But it is the same structure. We have a point in the plane. This is restricted to the 2-dimensional case, okay? So I have a point in the plane that satisfies the equation. That is, f of x0, y0 equal to 0 means that the point x0, y0 belongs to this curve, because this is a curve in the plane. The other theoretical point is that f must have continuous partial derivatives near this point. You know, this, we don't go into details about that, but this just means that it must be a regular function, as regular as needed, okay? As regular as needed. We will always assume this condition is satisfied. But the only thing to check here, so the first thing to check is that the point satisfies the equation. And the second thing to check is that the partial derivative with respect to y of this capital F of xy at this particular point must be different from 0, okay? Which means that the tangent to that curve must not be vertical. If these conditions are satisfied, then this equation defines implicitly a unique function y equal to f of x, lowercase f of x, near the point x0. Namely, this is important. If y is in fact f of x, this f of xy equal to 0 means f of x equal to 0, okay? Capital F of x, lowercase f of x, equal to 0, which means that you let x vary in its domain near x0. So it takes a value. Since y is a function of x, f of x takes another value, but the formula that relates x and f of x has a final value which is always 0, okay? Is that clear? This means that y is a function of x. And do you remember that this issue here is related to the curve defined in the plane by our f of xy equal to 0 is not vertical at that particular point. Because at that particular point, at the red point, for instance, if I have a vertical tangent, it's not possible to identify even a small circle, including the point, where this equation actually defines y equal to f of x, because f of x means that for each value of x, there is a unique value for y, but, okay, here, for each x, we have two different values for y. So this is the intuition. Okay, by the way, this is the most important thing for applications. Not only we know that a function exists, it is well defined, it is unique, but we can also compute its derivative. This formula is very common in microeconomics, okay? It's this is a derivative along a curve which is taken as the ratio of two partial derivatives of a two-variable function. The theorem concludes that our derivative of y with respect to x is minus the ratio between the two partial derivatives with respect to x in the denominator, with respect to y in the denominator, at the point xy, where of course y is equal to f of x. So this means that even if to compute this expression you need two variables, since y is equal to f of x, as proven in the previous point, this expression depends only on x, of course. Is it clear? Okay. In particular, at our point, to compute the derivative, it's just enough that you take the ratio of the two partial derivatives at that particular point. The assumption that the partial derivative with respect to y, which is important, means that the tangent to the graph must be non-vertical, and this is already discussed before. The right-hand side is a function of x. Example. The fourth remark, we don't even need to be able to solve the equation f of xy equal to 0 explicitly for variable y in order to be able to compute the derivative. This is what I mean. This is quite important. Look at this example, which is similar to another example in your textbook. Look at this equation, exponential of x squared y minus 3x minus 2y equal to c. C is a real parameter. Now, the first step, of course, this is not a curve in the plane. This is a family of curves in the plane because it depends on a number here, okay, a generic parameter. Find C such that x0, y0, 1, 0, so the point 1, 0 in the plane, x equal to 1, y equal to 0, satisfies this equation. This is just to highlight the fact that our point must satisfy the equation, okay? So we determine C in such a way that the point satisfies the equation. Second, once you have obtained C, check whether the equation defines implicitly y equal to f of x near x0 equal to 1, which is the abscissa here. Okay? This is the second question. Third, compute f prime of x0 at the point x0, where the function will have the value, will take the value y0, of course. First point, we must find C such that the point satisfies the equation. This means that C must be such that the left-hand side is equal to the right-hand side when we replace 1 to x and 0 to y, okay? This is the basic idea. Okay, replace 1 to x, this becomes minus 3, sorry. This becomes 0. And this becomes exponential of 0, which is 1. So 1 minus 3 must be equal to C. C is equal to minus 2. Okay? So C is equal to minus 2. So our two-variable expression that defines a curve in the plane passing through the point 1, 0 is this one. Okay? That clear? Okay. Now, since when we want to compute the derivative of this, we must compute the partial derivatives of f. F is the left-hand side. I hope you realize that these two doesn't matter for the derivatives, okay? So you can also look at just this part here. Okay, computing the derivatives. And next, we will check that this is 0 at our particular point, okay? This is, sorry, different from 0 at our particular point, because otherwise we cannot define. We have a vertical tangent, and we cannot define an implicit function. Okay, let me compute the two partial derivatives. With respect to x, it is exponential of x squared y times the derivative of the exponent with respect to x, which is 2xy. Okay? Minus 3. And this part is 0 when I take the derivative. The derivative with respect to y is exponential of x squared y times x squared minus 2. Okay? This 2 here. Now, in particular, the partial derivative of capital F with respect to y at our point, 1, 0, just replace 0 to y, and this becomes 1, but this is 0. Sorry, this becomes 1, but this is 1, so 1 minus 2 is minus 1. Is this different? Is that okay? It's different from 0, so this is the condition, the basic condition of the theorem to be checked. Okay, to be able to compute the derivative. You can even skip this condition, because when you compute the derivative, which is like this, if you don't have this condition holding, you cannot just compute the derivative, okay, because the denominator is 0. So you can just compute the derivative and, in particular, check that the denominator is different from 0. Now, I need also the numerical value of the other derivative, the one with respect to x at the point. So this becomes 1 times 0 minus 3. So minus 3. Okay. Now, what is the derivative of our curve in the plane at the point 1, 0? So the derivative, remember, this is lowercase f. This is the function implicitly defined by the equation. We don't have the expression of this function, but we can compute the slope of this curve at the point, okay? We can compute the derivative. F prime of 1 is minus, look at the formula, minus partial derivative with respect to x at the point divided by partial derivative with respect to y at the point. So minus 3 over minus 1, it is minus 3. So we don't know, for the moment, we know nothing about this curve, except the fact that it passes through the point 1, 0, and at this point, it has a slope equal to minus 3. Okay? How would you just try to compute other points where this curve, that belong to this curve, and other slopes. By selecting the values of one variable in the equation, here, this is our equation. If you select the values of one variable, then you can try to solve for the other variable, either analytically, if possible, or numerically, just by trials, okay? Just by trials. When you find points, or something which is close to the points that belong to the graph, you have the elements to compute the slope at these points, okay? So you can understand a lot about this. For instance, we use the point 1, 0 here. But what about a point in which x is 0? Now x is 1. X is 0 means I'm looking at the intersection of the curve with the other axis, the y-axis, okay? If you put x equal to 0 here, when x is equal to 0, this becomes 1, okay? 1 minus 0 minus 2y plus 2 equal to 0, okay? So it is a simple equation in y. So you can determine the value of y, the point where our curve crosses the vertical axis. And you can repeat the experiment and computing the slope at the point where our curve will cross the vertical axis, okay? So we will have 2 points and 2 slopes. Okay, the curve basically is this one. It's a very complicated one. You see, it's a very complicated curve. But basically, we just studied the behavior locally here, okay? Where we discovered that passes through the point 1, 0, and it has a slope equal to minus 3 here, okay? Is that clear? Oh, sorry. Bad network point, okay. You can repeat the experiment with the other. So basically, it crosses the vertical axis. You would find that it crosses the vertical axis at the point 0, 1.5, 3 over 2, okay? And then you can repeat the experiment there and look at the slope at that particular point. So this is, of course, the geometric interpretation of what we are doing. There is another example that you can try to work out. I don't want to present it extensively here, but you can just look at this. So just write down the equation of this two variable equation, okay? And try to solve this by yourself, okay? So it is the exponential of ay. So here a is a parameter. In this example, it is 0.5, 1/2, okay? Plus by, where b in this example is equal to 2. Minus x to the power of 3, plus 1 equal to 0. By the way, if you try here to solve, suppose that you put here 2 and you put a equal to 1/2. So you don't have parameters, you have numbers. There's no way to solve y as a function of x. And this is one of the main points. It's not possible to use algebra to make y as a function of x explicit. We're just interested in whether, apart from our ability to solve y as a function of x, this defines implicitly or not y as a function of x, okay? So this is the main point. If you do that, you discover that the point 1, 0, this would be the assignment of the exercise, okay? So the point 1, 0 belongs to the graph of this curve. Because if you replace here x equal to 1 and y equal to 0, you get a point that satisfies the equation. Clear? With the same rules used before, you can compute the derivative at the point of abscissa 1. Okay? And the derivative at the point of abscissa 1 is 8/5. But not only, I mean, now we have a point, which is 1, 0, and the slope at this point. We can build the equation of the tangent line. In order to build the equation of the tangent line, you need a point that belongs to the graph of the curve, of the function, and the slope at that point, okay? If I build the equation of the tangent line, I get this one. Y is equal to 8/5x minus 8/5, which is this dashed line here. And we can check actually which is this is the tangent line, okay? Is that clear? I mean, I invite you to write down this exercise here with A equal to 1/2 and B equal to 2 to check that the point 1, 0 belongs to the graph, to compute the derivative at the point of abscissa 1, okay, which is 8/5, and next, to build the equation of the tangent line, which is this one, okay? So it's not, I mean, it's not difficult. It's like the previous one. The only additional point is that we use the derivative to build the equation of the tangent line, because we also have the point. Okay. So this is basically what I mean. Sorry, this is the Google News. I don't know how to make it disappear this way. Okay. And finally, I want to point out that the theorem not only states that we can compute the derivative at that particular point, but also near that point. So we have a formula for the derivative in principle also near that point. Of course, we don't know the expression y equal to f of x. So we must work out the derivative in this way, okay? But this also holds near the point x equal to x0, where y is equal to f of x0, okay? So this also holds near the point x of x0, y0, where y0 is y equal to f of x0. We have an expression in two variables which must be interpreted as a function, because y is equal to f of x. This may be difficult in its theoretical statement, this one, but it is quite intuitive graphically, okay? Here is another example. This is a very popular example, which also highlights some properties of these functions. And so basically, in this case, we want to deal with a level curve of this two-variable function, which is a power function in two variables, which is a Cobb-Douglas function. We want to deal with one of its level curves using the theory of implicit functions, even if, of course, we are able to solve y as a function of x now, okay? So consider these two variable functions. Z is equal to 5 times cubic root of x times square root of y, which is my capital F of xy. Consider the point x0, y0, which is 8, 4. Okay? So x equal to 8 and y equal to 4. What is f of x0, y0? Just replace 8 and 4 here, and we get 5 times cubic root of 8 is 2, square root of 4 is 2, again, 5 times 2 times 2, it's 20. Now, of course, since z0 is 20, if I write here 5 times the f of xy equal to 20, okay, this is, by definition, a level curve of my function passing 4. Is this point clear? This is quite trivial in a sense, but I mean, by definition of a level curve, is the combination of all values of x and y, giving the same final value of the function. In our example, the final value of the function must be 20, okay? In particular, one point of the level curve will be 8, 4, because we know that f of 8, 4 is 20, okay? But there will be many other points in the plane, giving as final value here 20, okay? So f of x, y, which is this one, equal to 20 is a level curve at height 20 of this particular two-variable function. So this is a two-variable equation in the plane. I could write minus 20 at the left hand side and equal to 0, which is the same. We want to compute the derivative along this level curve at the point x0, y0 equal to 8, 4. We can, I suggest, as an exercise, I will leave you the direct method. Direct means just, suppose that you don't know the implicit function theory. You just want to solve explicitly this, where y is an explicit function of x. Now remember that in this point, x is equal to 8, and I will compute the derivative of this one variable function at the point of abscissa 8. Okay? You are invited to do that, which is a one variable exercise, and to obtain the same result that we get here. Now, we want to compute the derivative along the level curve using the implicit function derivative formula. Okay, so I compute the partial derivative of f with respect to x. Okay, it's 5 over 3 times x to the power minus 2/3 times y to the power 1/2. But just remember the structure of the partial derivatives of this two variable function. We discussed them many times already. It's 1/3 is alpha, okay? It's exponent of x. So it is 1/2 divided by x times f of xy, where f of xy is the original expression. This is a very useful tool to remember. Similarly, the partial derivative of f with respect to y is this one, but it can also be written as 1/2 divided by y times f of xy. So the two partial derivatives will have a common factor here, which is capital F of xy. Now remember that when you take the implicit differentiation formula, you take the ratio of these two partial derivatives. So if they have a common factor like this is very, very useful, okay? Now, what is the partial derivative of this function implicitly defined by this two variable equation? Y is a function of x. It is the partial derivative with respect to x over the partial derivative with respect to y. So if you go here, this will disappear. This factor capital F could disappear in the numerator and denominator. And we are left with minus 1/3 divided by 1/2 times y over x. So minus 2/3 y over x. This so in a sense, this is a very simple expression, okay? If you don't use this formula, you get a more complicated expression, okay? Is that clear? Because y is a function of x, it will have a quite complicated expression obtained by solving this one in terms of x. But in this case, we have this message. The derivative at any point x of the domain where y is such that xy lies on the level curve, of course. It's not the generic y here, okay? As this structure, minus 2/3 times y over x, the ratio between y and x. Now, we can, for instance, evaluate this at our point, which is 8, 4. So it becomes minus 2/3. Remember, x0 is 8. So put 8 here. y0 is 4, because we already proved that our point belongs to the curve. So we have minus 2/3 times 1/2 and minus 1/3. Okay? Very easy for these particular functions. And this is quite a common property for these two variable functions that are used in microeconomics, utility production functions, not just the Cobb-Douglas, but many more. For instance, one which is more complicated than this one, but has similar structural properties, which is called CES. Okay, there is another function in two variables, which is called CES, constant elasticity of substitution. And it has some, it looks like quite a complicated function, but when you deal with these implicit function derivatives, you get relatively simple formulas here. Again, based on this ratio. Okay? So just keep in mind that this is useful even when you can solve, actually. Often it's not convenient to solve y as a function of x. So what is the meaning of our exercise? We have a function of two variables, which is a function of x and y. If we impose a given value for z, which is the third variable, we have a level curve, which is like this. Okay? It is a level curve which is like this. We have a point that belongs to this curve, which is 8, 4. And we just computed the slope of this curve at the point 8, 4. Okay? Obtained in this way. So basically, the exercise that I leave to you is just to check also our result, is to solve explicitly this one for y. Then we will have a one variable function, and then we want to compute the partial derivative of this at the point of abscissa x0. I hope this is clear enough. I mean, being able to deal with this kind of computations, I guess it is quite important. Okay? Because they are, in a sense, they are basic models, basic ideas, but these computations are very typical. Okay, so just try to also to do that with a different function, a different, for instance, power function, for instance, x to the power of 1/5 and times y, I don't know, okay, or y squared, okay, and try to compute explicitly a level curve. Okay, identify a particular level curve and a point that belongs to that curve. Try to solve it explicitly, compute the derivative explicitly and implicitly. So you have a way to check your result. There is a general property behind this, which is this one. This is a slightly more general model, okay, that shows that we can easily understand in general why the two formulas lead to the same derivative. So take a general multiplicative model like this, capital A times x to the power of alpha times y to the power of beta. Alpha and beta are positive exponents. The level curve of f, capital F, at height z0, z0 was our previous 20, okay, which is equal to f of x0, y0, which was 8 and 4 in our previous example, has equation f of xy, which is this one, equal to z0. What is z0? Z0 is just the value, since x0, y0 is supposed to belong to this curve, okay? Z0 is the value we're obtained by replacing x0 and y0 here, okay? So what are the partial derivatives of f? This is also to recap our knowledge of this function. One is this one, which can be written as alpha over x times capital F, the original function. The other one is this one, beta over y times capital F, again. It's clear that if I take the ratio between the derivatives, that is, if I compute the derivative of the implicit function, I get this ratio. So this is minus alpha over beta times y over x, which is exactly as in the previous example. Okay, so this is very general. And it holds for any function of this type and for any positive exponents. It's a very general formula. In particular, at the point x0, where the second coordinate is y0, we have minus alpha over beta times y0 over x0. Now, how can we see immediately that this is also the result that we obtained by making y explicit and computing the derivative of a one-variable function? We can do that by just okay, so this is just a graph similar to the previous one. Okay, so the point x0, y0, this is our level curve. All of these level curves have a shape like this. They are negatively sloped, convex, and as x tends to 0, y tends to plus infinity. As x tends to plus infinity, y tends to 0. I suppose that this is not part of the mathematics course, but it is related to basically to the marginal rate of substitution of the two goods, the quantities of which are modeled by x and y. This is basic microeconomics, okay? Anyway, so this is a very typical shape. Decreasing, concave, when x tends to 0, y tends to plus infinity. When y tends to plus infinity, or better, when x tends to plus infinity, y tends to 0, okay? This is the slope of the level curve at x0, y0, formula that we obtained in the previous, which is the slope of this tangent line. Suppose now that you solve the equation of the level curve explicitly, okay? So you want to obtain y. Y had exponent beta. So first you divide z0 divided by a. You divide. So you have this equation, okay? This one equal to z0. Divide by a first. Multiply both sides by x to the power of minus alpha, and then take the power of 1 over beta. And you make y explicit. This one. It becomes, this is a constant, z0 over a to the power of 1 over beta times x to the power of minus alpha over beta. Now we want to compute its derivative and evaluate the derivative at x equal to x0. What is its derivative? It is this one. This is a constant, z0 over alpha to the power of 1 over beta times the derivative of this, which is minus alpha over beta times x times, x to the power of minus alpha over beta minus 1, okay? But what is this quantity in red? Z0 over alpha to the power of 1 over beta times x to the power of minus alpha over beta is just y. If you add minus 1 here, it's y over x, okay? It's y over x. So basically, this is the quantity. This times this. This times this, the first factor times the last factor is y over x, but then we add minus alpha over beta. So minus alpha over beta y over x, which is precisely the formula that we obtained before, okay? So it's just to show you in general that this holds. Okay, so derivatives along level curves are a very, very important and common tool in economic analysis. Okay, now I just want to show you one thing, and then I will start with constraint optimization. And this thing is related to the formula for the derivative. This is a very appealing formula, okay? Just compute the two partial derivatives, take the ratio and change the sign. How can we obtain this formula? Is there an intuitive way to figure out why the derivative of the implicit function is this one? This is the main point. And there is a it's rigorous, but it's just one line of proof. The proof is one line. So it's very instructive because it is an exercise on the chain rule, okay? Okay, so let me show you why it works in this way. So I don't write everything again. I have an equation of this type for f of xy equal to c, which is exactly the same for the purpose of computing derivatives. This is the same. Now suppose that y is a function of x. Let me call it, okay, let me call it h of x, because next I will use h to denote this function in my slides on the constraint optimization. H of x near. So of course, this also passes through the point x0, y0, so we have that. F of x0, y0 is equal to 0, for instance. So this means that this point belongs to the curve. Suppose that we know that this defines a function h of x near x0. Remember what we wrote before in the comments to the main result, then f of x, h of x is equal to 0, because y is equal to h of x, near x0, okay? This means that I have two sides. One is identically 0 for any x sufficiently close to x0. And this is a complicated expression in x, but it is a function of x, okay? This is just a function of x, because it is x and h of x. So if I take this, also if you put c here, if I take the derivative of the left-hand side with respect to x, what do you expect the result is? This is a function of x, but if I compute the derivative of this function, the result would be 0, because the derivative of 0 is 0. I mean, this is a function of x. You let x vary. H of x varies along with x, okay? But the combination of the two into capital F is always 0. This is what is written here, okay? So if you compute the derivative of this must be 0. So call this function, I don't know how to call it, maybe phi of x. We can conclude that the derivative of phi of x with respect to x is equal to 0 by definition, by construction. But what is the derivative of phi with respect to x? Remember the chain rule. You have a function of two variables, but each variable, the first variable is x, the second is y, but each of them depends on x, okay? This is one of the two particular types of chain rule that hold for multivariable functions. Remember the formula to solve this? This is equal to, first take the derivative of capital F with respect to its first argument, okay, times the derivative of x with respect to x. All of the two arguments depend on x. And in particular, the derivative of f of x with respect to x is 1, plus the partial derivative of f with respect to y times what? The derivative of y with respect to x. Y is h of x. h prime of x, and this must be equal to 0. Remember that we don't know h prime of x, but we know this and we know this. So we obtain that h prime of x is equal to, change the sign, take the ratio, okay, which is the formula for the implicit function derivative. Okay. So this is basically, this is the proof of the formula. This is already the proof. Next, I mean, we should put more details and more discussion, but this is the core of the proof. And it is based on the chain rule for a two-variable function in which each of its variables depend itself on another variable, okay? In our examples, we had t here, okay? Remember t and h of t. Here it is called x. It is the same. Okay. Now, second step is constraint optimization. If you have the part on these basic results on implicit functions clear enough in your mind, you can, I guess, you can understand everything about constraint optimization. Unfortunately, the only point with the simple exercises on constraint optimization that I regard as basics, but yet important, is the algebra. So there are. I'm also going to show you some tricks to solve these exercises without mistakes, okay, and to arrive very quickly at the solution without useless and computations, heavy computations. Okay, so what is a constraint optimization problem? We restrict ourselves to equality constraints. Okay, I will show you what equality constraints means and what inequality constraints means, of course. We don't deal with inequality constraints, just equality constraints. Many problems with inequality constraints can be reduced to problems with equality constraints, just because it can be shown that the solution lies at a point where we have equalities and not inequalities, actually, as in the original problem, okay? So many problems, in principle, should be formulated with inequality constraints, but they can as well be formulated with equality constraints, and the solution will be there. So we have to maximize with respect to variables x1, x2, and xn, expressed in the form of a vector x, or possibly minimize with respect to the same vector of variables, it depends on the problem, a function of n variables under a number of equality constraints. Okay, our function of n variables is denoted as an expression that involves x1, x2, and xn. Okay, so its value will change according to our choice of these decision variables, but we have constraints. We cannot select any possible combination of x1, x2, and xn. We have to select only those combinations that also satisfy this system of equations. This is a general form. Another expression that involves x1, x2, xn must be equal to b1. Another expression that involves the same variable must be equal to b2, and so on and so forth. Okay? So we have n variable and n equalities and equations that these variables must satisfy in the optimal in the solution. Okay? Usually m is less than n. And the reason is that, just in simple words, so the number of conditions that you put on your variables the number of conditions that you put in your variables in terms of equalities that they need additionally to satisfy must be less than the number of the variables, because in simple words, every time you impose an additional equality, you reduce, you have one less degree of freedom in your choice, okay? So suppose that you have just an equality here. You cannot select here any values for x1, x2, and xn. You can select x1, x2, up to xn minus 1, but xn must be chosen such that this holds, okay? Every time you impose an equality constraint, you decrease the number of degrees of freedom of your problem. So in order to have at least 1 degree of freedom, your m must be less than n. This is a very, in a sense, very simple explanation. Of course, in reality, that's not always true, okay? But in principle, m must be less than n. Typical problems, m is less than n. Of course, try to imagine a situation in which they are only formally m different constraints, but they are actually the same constraint, for instance, okay? Because, for instance, the second is the first multiplied by 2, and this one is the first multiplied by 3, okay? So they are m, but they are in fact 1. So in this case, you could have even more constraints than variables, okay? That's the main point. But if they are true constraints, n must be less than n. Trivial example, maximize the product of x and y subject to 2x plus y is equal to 100. This is one example which is worked out in your textbook. That could represent maximizing the utility from consumption of two goods in quantities x and y subject to a budget constraint. A budget constraint means that your monthly budget is 100, for instance, and it costs 2 euros every unit of good x, costs 1 euro every unit of good y. So this is the monthly expenditure, and this is the monthly budget, okay? And we impose an equality. This is a classical example in which you should, in principle, impose an inequality here, less or equal to 100, okay? Why should I spend all of my budget? I want to maximize my utility, and the constraint is that the budget must be enough, okay? So less or equal to, but it can be shown that the solution in this particular problem will be at the boundary. So in a situation in which you spend all of your budget, okay? So this is the why, and this also for in many cases with many variables, whenever our utility function, our function to be maximized, is strictly increasing in all the variables, okay? If our function is strictly increasing in all the variables, you always improve your situation by consuming more of each good, and this means that you will your budget will be we arrive at a saturation, okay? Okay, so in order to derive the Lagrange function for this problem, and in general, and the conditions for optimality, it is enough to look at this problem as a problem which is only formally in two variables, but in fact, it is a problem in one variable, because from the second equation, x and y cannot be chosen independently. Y will be 100 minus 2x, okay? If you select x, then y must be chosen in a way that this is equal to the budget. So y will be equal to 100 minus 2x, okay? So y is in fact a function of x. So you don't have a function in two variables here and one budget constraint. You have a function in one variable and no constraints at all, because this is incorporated here. So you can write the problem as maximize f of x equal to x times 100 minus 2x. Clear? So this is a problem in one variable. Solve this problem. First derivative, 100x minus 2x squared. Okay. Necessary condition for x star to be the maximum is that this derivative is equal to 0. So 100 minus 4x equal to 0. X is equal to 25. Okay, this is the solution. Now remember that y is 100 minus 2x, so y is equal to 50. Okay, so the optimal solution is to consume, in order to maximize the utility, to consume 25 units of good x and 50 units of good y. Okay, now keep this in mind because so what we did here is to make this 2x plus y equal to 100 with the language of the previous general language is g of x, y equal to b. Okay, we have only one constraint and two variables. G of x, y equal to b. 2x plus y equal to 100. This is g of x, y. This is b. Okay? What we did is to make y explicit in this two-variable equation. Here we made y explicit and we solved the one-variable problem. But in principle, we don't need to make y explicit here. It may be difficult to obtain y as a function of x, or it may be useless, or it may just be impossible, okay? But anyway, it's clear that under certain conditions, our constraint, g of xy equal to b, which is this one, g of xy equal to b, will define y as a function of x. Is that clear? Is it clear why the implicit function theorem is so important to find a clean way to solve constrained optimization problems? This is the reason. The constraint is formulated implicitly, but through the constraint, we have in fact one variable which is a function of the other variable. Okay, so the usual solution method, now I'm going to show you the usual solution method, which is the Lagrange multiplier method, and next I will explain why it works this way. So when we solve this kind of problems, we don't make y explicit in the constraint, okay? We don't do that. We use the Lagrange multiplier method. So our original problem is to maximize f of xy or minimize f of xy by choosing x and y in such a way that x and y also satisfy this constraint, g of xy equal to b. This is the basic case. Two variables, n is equal to 2, and one constraint, m is equal to 1. Two variables, one constraint. Okay. Okay, so the usual solution method is to use the Lagrange multipliers, okay, and the Lagrange function. This is the same structure as the previous problem. G of xy was 2x plus y, b was 100, f of xy was x times y. What we do is to build another function which is called Lagrange function. It is an auxiliary function, and it depends on the textbooks. You can regard this as a function of two variables as well, x and y, where there is an additional important quantity which is treated as a parameter, which is called lambda. Lambda is a Greek letter. Or in some textbooks, this is regarded as a function of an additional variable, lambda, so it is regarded as a function of three variables. Your textbook treats lambda as a parameter. So it is a two-variable function, and you see here that lambda is separated by the true variables. This is just a parameter, okay? So the expression of this Lagrange function is the original function to be maximized or minimized, f of xy, plus lambda, which is the parameter, times what? B minus g of xy. What is B minus g of xy? Think about the original economic problem. Is the budget minus your expenditure, okay? So what is left from your budget after deciding your expenditure? B minus G of xy. The first observation, the first remark is that lambda is called the Lagrange multiplier. In general, we have as many different Lagrange multipliers as the number of constraints that we have, okay? So in this example, when building the Lagrangian here, we will have an additional term for this one with an additional Lagrange multiplier, another for this one, and so on and so forth, okay? So for instance, since we have problems with many variables, you must just be able to understand the notation. If the problem is maximize by choosing x, f of x, okay, subject to, you may find this way to express the M constraints. G, this is usually in bold or underlined, G of x equal to B vector, which means G1 of x is x1, x2, xn equal to B1, okay? G2, x1, x2, so on and so forth, xn equal to B2, up to the m, gm of x1, x2, xn equal to bm. So these m constraints are expressed in this way. This is a vector-valued function. So if you put x into this function, you don't get a number, you get a vector, okay? An array of numbers, which are g1, g2, and gm. This is a vector-valued function with m components. So this is just for the notation, okay? Just don't get lost when you see this notation. It is our previous problem. In this case, the Lagrange function would be like this. It would be a function. Sometimes the Lagrange function is denoted in this way, a kind of calligraphic L. L of x vector, lambda vector, which will be lambda 1, lambda 2, up to lambda m. We will have a different Lagrange multiplier for each constraint, okay? And that would be f of x. Let me write this extensively. Plus lambda 1 times. Imagine that here you have different constraints, and this can be interpreted as a kind of budget in any case, okay? Lambda 1 times b1 minus g1 of x1, x2, up to xn, plus lambda 2 times a similar term, okay? Plus lambda m times bm minus gm of x1, x2, xn. So nothing changes, in fact, when you have many variables and many constraints. You must remember that you have as many Lagrange multipliers as the number of equality constraints, okay? And the Lagrange function will be written in this way. Clear? Okay. Now, another thing which is important is that all the points xy that satisfy our constraint So if gxy is equal to b, then this part is 0, okay? So we get back the original function, f of xy. Okay. And then the third step is to solve this system. The partial derivative of our Lagrange function with respect to x, which is this one, must be equal to 0. This is a kind of computing the two partial derivatives of the Lagrange function with respect to x and y, and impose that they are equal to 0, like the first order condition for our optimization problems without constraints, but now we are working with the Lagrange function, okay? They are necessary condition for a maximum or a minimum with constraints, okay? So we have these two partial derivatives equal to 0, and the third condition is g of xy equal to b. So our points must also satisfy the constraint. Why is that? Why do we need three conditions? Because lambda is unspecified here. If we want to get a solution, here we don't have actually two variables, two quantities to be determined by this system. We have three, x, y, and lambda. So we need three conditions, okay? The first two conditions must be interpreted as the partial derivatives of the Lagrange function with respect to x and then to y. Why is that? Because what is the partial derivative with respect to x? It is partial derivative of f with respect to x, lambda b is a constant, minus lambda partial derivative of g with respect to x. And the same for y. So we have these conditions. Three equations in three unknowns, x, y, and lambda. And what can be shown, which is easy in some basic cases, is that the solutions that we get for this system, the solutions means are triples, okay? A value for x, a value for y, and a value for lambda is a solution to this system. In principle, we may have more than one solution. In our problems, we will generally have one solution. These triples include the solution to our original problem. So if you get, for instance, that your solution to this system is 2, 3, and lambda equal to 1/2, okay, so 2, 3 is the solution to your original problem. Okay, so the pair xy is the solution to your original problem. This is the power of this, the use of the auxiliary function, which is called Lagrange function. So a few words on why things work this way. Okay, this is a first example, which is very easy. I mean, build the Lagrange function. This is our previous example, build the Lagrange function, xy plus lambda, budget 100 minus 2x minus y, compute the partial derivatives with respect to x. With respect to x is y minus 2 lambda equal to 0. With respect to y is x minus lambda equal to 0. And then the third equation is the constraint, 2x plus y equal to 100. This is a very simple example, but here already you see the structure that you have to look at to solve your model. Just try to make lambda explicit in each of these equations and then to equate what remains on the other side. So here you get lambda is equal to y over 2, and here you get lambda is equal to x. So y over 2 is equal to x, y is equal to 2x. Replace this into the constraint, which is linear in this case, for x equal to 100, and you get also lambda equal to x as a final result. And you get x 25, y 50, and lambda, which is equal to x, is equal to 25. Now we don't know what lambda means. What is the meaning of this numerical value that we find for lambda? Because from our perspective, so far, that was only an auxiliary tool, okay? But it has a strong meaning in economic terms, okay? Which is related to the sensitivity analysis of the solution. What about using the Lagrange multiplier? What about deriving the Lagrange multiplier method in the general case? It's easy if you keep in mind this example. So this is just 2 pages of, let's say, derivation of the Lagrange multiplier rule. In general, we have this, and we have a constraint like this. Suppose that we don't want, or we are not able to solve y as a function of x. We want to work out this constraint implicitly. We just have to assume or to check that g of xy equal to b defines implicitly y equal to h of x near the solution of our optimization problem. This is something that we assume in advance. It can be checked later, okay? But we must assume it in advance. If this is true, okay, we can compute the derivative. H prime of x is minus the derivative of g with respect to x over the derivative of g with respect to y, okay? This is an implicit equation in 2 variables. This is the derivative, assuming that y is a function of x, defined by h of x, its derivative is this one, provided that the denominator is different from 0. This comes from the implicit function theorem. Now, this is another application of the chain rule. If this is true, our function to be maximized is not actually a function of 2 variables. It is a function of a unique variable, x, right? Because in our initial example, this was in fact a function of a unique variable, capital F of x. We can do the same here, but the only difference is that we don't know the expression of this h of x function, okay? So capital F of x is this one, f of x, h of x. We can compute, if this is a 1 variable function, the condition for a maximum is derivative equal to 0, okay? Compute the derivative, use the chain rule as before. The derivative of f with respect to x times 1 plus the derivative of f with respect to y, which is the second variable, times h prime of x, which is the derivative of y with respect to x, okay? So what is this h prime of x? This h prime of x is this one, okay? So replace to h prime of x this green part, sorry, to h prime of x, replace this with this fraction, okay? Which is this one. Now, look at the green part, call it lambda. This green part is the partial derivative, is the ratio between the 2 partial derivatives with respect to y of f and g, respectively. Call this lambda. If you call this lambda, you get that the condition for an optimum of a 1 variable function can be written as partial derivative of f with respect to x minus lambda partial derivative of g with respect to x is equal to 0, okay? Which is the first condition that you find here. Okay? Now, of course, we can write this in this way because we arbitrarily define lambda equal to this one. So we should write somewhere that we define this one to be equal to lambda. We should write this here, multiply both sides by the g over the y, and move to the left, and you get the second condition here, okay? Second condition is this one. This one. And the third condition is just a constraint that must be satisfied. So this is why, if we just consider our 2 variable problems with 1 constraint as a problem in 1 variable, and we just write first derivative equal to 0 of this 1 variable function, even if we don't know the expression of this 1 variable function, we get this system of 3 conditions. And this is like working with an auxiliary function, which is called the Lagrange function. So basically, this is this is the proof of the conditions, the necessary conditions for an optimum of a problem with 2 variables and 1 constraint. Okay? So what we have done before shows that if x star y star solves our original problem, then this set of conditions must be satisfied for some number lambda. And this number lambda here has been found to be this one. For instance, you can check that in the previous example, our lambda is equal to 25, which is precisely equal to x. So if you don't feel, I mean, I think it is important to have shown this. If you don't feel trained with this kind of theoretical proofs, don't worry, this is not so important. This is to justify that basically building the Lagrange function and setting its derivatives equal to 0, okay, leads to a solution, and embedded in that solution is the solution to our original problem. Example, with solution and interpretation of lambda. This example is again with the power function in two variables and a linear constraint. But it has two additional features. One, it is parametric. So here I don't specify the budget. I want to get my solution as some mathematical expressions in terms of the budget. So it's a family of problems, okay? Not just a single problem. And second, I will make one step further and try to interpret what you obtain for lambda in the solution. Okay, I want to maximize 2 square root of x times y subject to this linear constraint 3x plus 2y equal to m, where, for instance, m is equal to 27. But I want to find a solution for general m. I build the Lagrange function 2x to the power 1/2 y plus lambda times what? The budget minus the expenditure. It's always useful to look at the constraint as the expenditure on the left and the budget on the right, okay? It's always very useful. So here is a kind of consumption of, this is the expenditure, means using your budget for providing resources, and this is the total amount of the budget. Okay, so it's useful to look at a constraint in this way many times. So plus lambda m minus 3x minus 2y. The partial derivatives, okay, with respect to x is 2y times 1/2 x to the power minus 1/2 minus 3 lambda equal to 0. With respect to y, it is 2x, 2 square root of x minus 2 lambda equal to 0. Okay, so we can use this strategy to solve this equation. This is one among the possible strategies. We can, for instance, here, we obtain lambda is equal to square root of x. Okay, lambda is equal to square root of x. So in the other equation, we have 3 lambda. So I write 3 square root of x, okay? Then I have an expression x to the power minus 1/2 y minus 3x to the power 1/2 equal to 0. If I multiply both sides by square root of x, this becomes 1, and this becomes x. So y is equal to 3x, okay? So one equation is y is equal to 3x. Then we have the linear constraint equation. Replace 3x here. It becomes 9x equal to m. And then we have as a byproduct, lambda is equal to square root of x. And this means that x is equal to m over 9, okay? And y is equal to m over 3, okay? This is a solution of a parametric problem. The optimal amount to be consumed of the first good is the total budget divided by 9. Okay? This is a quantity. The optimal amount to be consumed of the second good is the total budget divided by 3. And lambda is equal to x to the power of 1/2, which is 1/3 square root of n. For instance, if m is equal to 27, sorry, there is a mistake here. If m is equal to 27, x will be equal to 3, and y will be equal to 9. So this is not 2, it is 9 here. And lambda is 1/3 square root of 27, which is square root of 3. So what is, first of all, what is the interpretation of lambda? This comes with no proof, but the proof is quite long, but we can check this in the example. In order to interpret lambda, what the value that we get for lambda in the solution, which is not just a number that comes as a byproduct of our mathematical exercise, it has a meaning related to this problem. In order to interpret lambda, we have to build the value function. Value function is a general concept. It holds for static optimization, like this one, simple problems in 2 variables and 1 constraint. It holds for constraint optimization with many variables and many constraints. It holds for unconstrained optimization as well. It holds for dynamic optimization. And the meaning is always the same. You have a problem that depends on one parameter, like in this case, or more parameters, okay? Can you imagine a problem with more parameters? Instead of just having m left as a parameter, we might have the price of the first factor of the first good, which is P1 here, for instance, and or the price of the second good, which is P2. So we may have 2 additional parameters in this example. So our solution would depend on the 2 unit prices and the budget. Clear? So you have a problem of optimization that depends on parameters. You get the optimal solution, like here. The optimal solution depends on the parameter or on the parameters, which are unspecified in your problem. But then you have your function to be maximized or minimized. So you put the optimal solution here inside. But since x and y depend on the parameters, also the maximized value of your function will depend on the same parameters, okay? Okay, so the maximized value of a function or the minimized value of the objective function. Briefly, the optimized value of the objective function, regarded as a function of the parameters, is called value function. Okay? So the value function, you saw your problem, you found the optimal decision, but your optimal decision depends on the parameters. You put the optimal choice into the objective function, you get an expression, maximized, okay? But it depends on the parameters. This is called value function. In our example, the value function is f, the 2 variable function, this one, to be maximized, in which I replaced x with x star of n, this one, and y with y star of n, this one. Clearly, here I obtain a function which is of 2 variables that becomes a function of my parameter at the end, okay? Here, in the optimal solution, it becomes a function of 1 parameter or more parameters, if there are more parameters unspecified. This is called the value function, and if we are able to build this function, we can study immediately what happens to the maximized value of our objective, for instance, if we change the budget. Clear? Because it's enough to compute the derivative of the value function with respect to the budget. If we have more parameters, we can see what happens to the maximized value of the value function if we change one of these parameters. if the price of good 1 changes, the price of good 2 changes, okay? If the parameter is the budget, that is, if the parameter is what is on the right-hand side here, then we have this powerful result. The derivative of the value function with respect to the budget, so the constant term of the constraint on the right-hand side, is just the optimized value of the Lagrange multiplier. It's just the value of the Lagrange multiplier at the solution. Okay? This is general result. So the value of the Lagrange multiplier of the solution has a meaning in terms of sensitivity analysis, which means that suppose that my budget changes, what is the derivative of the maximized utility, in this case, with respect to the budget? It is just lambda. Okay? We can very quickly check this with our example, and then we will take a break. We can check this with our example immediately, because since the solution is this one, we can easily replace the solution into the function here and get f star, the value function, in terms of m. So what is f star of m? It is 2, our function, times the square root of x. Square root of x is the square root of m over 9 times y times m over 3. So it is 2/3 square root of m times m over 3. Okay? So it is 2 over 9 times m to the power of 3 over 2. Compute the derivative of this function with respect to m. It becomes 2 over 9 times 3 over 2 times m to the power of 1/2, which is 1/3 square root of m, which is exactly the value of our lambda in the optimal solution. And of course, apart from this is one of the results about the sensitivity of the solution, just one of the results. There are many more. All of these theorems, this is one of the most natural, let's say, side results for optimization, which is called comparative statics of the optimal solution. All of this area of the theory is called comparative statics of the optimal solution. This is one of the most elementary results. All of these results are called also envelope theorems. Envelope theorems. By the way, of course, I don't want to prove this, but if you look at the structure of the value function here, f of x star of m, y star of m, if you want to compute the derivative of this with respect to m, you have a function of 2 variables, but in fact, each of these variables depend on a unique variable m, so in principle, that will be again an application of the chain rule. This will be again an application of the same chain rule that we used for the implicit function theorem. But of course, if you are interested, all of these proofs are in your textbook. Okay, so for instance, if this is just an exercise, an additional exercise, but if our budget is m equal to 27, okay? And we suppose that our budget, so we found the solution in this case. It is x equal to 3, y equal to 9. Remember that we have a mistake here. X equal to 3, y equal to 9. Suppose that our budget changes to m prime equal to 30, not 27, it is 30, the budget. If we want to approximate the change in the maximized value of our objective function, we can use, for instance, the differential, which is the derivative, but the derivative is lambda, okay, times the change of the variable m, okay? So this is the linear approximation to the change of the value of our maximized objective function. So in this case, we would get 5.196. Okay? why is lambda star equal to 3? Because in general, we have lambda star equal to 1/3 square root of m. If m is equal to 27, at that particular value of the budget, the derivative is equal to square root of 3, okay? What is the true change of our value function? Here we were lucky because we were able to compute the true value function. So we can just evaluate the true value function, which was this one. The true value function was this one. We can just evaluate this at 30 and then subtract the value at 27, okay? Like this. And we obtain, I computed the two values, and the true change is 5.338. The linear approximation to the change, which is called differential in one variable calculus, is just the one we found here, 5.196, okay? So it's close enough to the true change. Okay, so this is just to illustrate the use of this as an approximation tool for sensitivity analysis. But the important thing to remember is that the derivative of the value function with respect to the budget is just the optimal value of the Lagrange multiplier at the solution. Okay. Next, I will show you after the break another very quicker, faster way to compute the solution to this problem, and then more examples, Okay, let's take a 10 minutes to 15 minutes break. See you again in 15 minutes. Okay. Okay, we now start again with our example, just showing you the just a quicker way to solve it, which is because we have a usual structure, Cobb-Douglas function, and a linear constraint, which is very common. Okay, so basically, if instead of writing things like this, instead of computing the derivatives and then trying to use the fact that lambda can be expressed in terms of x and next replacing the other equation, we can use a more interesting and general solution strategy, which is that of computing the derivatives and then obtaining lambda in each of the two equations. In particular, if you remember the structure, the derivative with respect to x of our function will be 1 over 2x, so 1/2 divided by x, times f, where f is the original function, minus 3 lambda. And the derivative of the Lagrange function with respect to y will be, remember that y has exponent 1, so it is 1 over y times f minus 2 lambda. And both of them equal to 0 plus the constraint. If we obtain lambda in each of these equations, you get an easier way to solve the system, because lambda is equal to f over 2x times 1/3, but lambda is also equal to f divided by y times 1/2. Okay, so if you equate these two, f disappears, you can simplify f, and you get 6x is equal to 2y, that is, y is equal to 3x. And then 3x plus 2y is equal to m. Okay, so this is maybe a more convenient way to solve these kind of systems whenever you realize that the objective function is Cobb-Douglas and the constraint is linear. But also when, I mean, if the objective function is Cobb-Douglas and the constraint is linear, this is the easiest way to solve the problem. And also another thing is the representation of the solution. The function xy, which is the objective function, has level curves that can be written as xy equal to c, that is, y is equal to c over x. So they are basically equilateral hyperbolas like this. Graphically, our solution is qualitatively here, x equal to 25, y is equal to 50. And the constraint, 2x plus y equal to 100, is this negatively sloped red straight line, okay? Passing through these points. You may remember that graphically, the solution of this kind of problems lies at the tangency between the equation that represents the constraint, which is this one, and one of the level curves of the objective function. So this is the graphical interpretation. The optimal solution satisfies the tangency condition between the constraint curve and one of the level curves of f, the objective function. Okay? Why is that? Because I don't want to prove also this, but it is very easy. What is the stating this? The tangency between one of the level curves of f and the constraint curve means that the slope of the constraint curve and the slope of one of the level curves must be equal, okay? Because they are tangent to each other. This is the slope of the constraint curve. It is the slope of the level curves, not just one. Any level curve has this slope expressed in general. So why is this the same as the first order conditions of the Lagrange function? Because if you remember how, imagine that now you multiply both sides by this quantity, okay? It disappears from this denominator and it appears here, okay? Then you divide both sides by this quantity, which disappears from the denominator here and appears here. And here you get a quantity that we defined lambda in the previous derivation, and here you get the other way we define lambda in the previous derivation, okay? So basically, the condition of the tangency can be easily rewritten as the two conditions that include lambda. So basically, the condition on the tangency can be worked out and give rise to a system of two equations. One is this one, and one is the other one, okay? So if we couple the condition on the tangency, which is equivalent to these two conditions, to the fact that our point must belong to the constraint, we get immediately this graphical interpretation. The point belongs to the constraint, that is, it lies on the red line, and at this point, the red line is tangent to one of the level curves of our objective function. So this is basically the idea behind the graphical interpretation of the solution as the usual tangency condition or the usual tangency point. And this is so strong and so established in the way basic microeconomics is illustrated that instead of working with the Lagrange function, many textbooks work directly with the tangency condition. So they write, instead of these two equations, they just write this one, okay, in the system. They solve a system of two equations in two unknowns. But now lambda has disappeared from here, okay? So you have two equations and two variables. So this is the way many times, if the problem is simple, it is solved in this way. Tangency condition plus constraint. Look at this example. This is a slightly different example, and it allows me to illustrate the second order conditions for an optimum. Remember that in unconstrained optimization, we have also to check concavity or convexity at the solution. There is a way to do that here as well. There is a strong result, and our problems will all fall within this case, okay? The problems that we will solve, which is the most common case. I will illustrate this statement in connection to this example. Suppose that now we want to maximize a linear function subject to a non-linear constraint. So our f of xy is x plus 2y, so the sum of x and the double of y. But x squared plus y squared must be equal to 9. If we write the Lagrange function, this is a maximum problem. The structure is different, but we have to write down the Lagrange function, x plus 2y plus lambda. So regard this as a budget. This is no longer a budget. I mean, we don't have this interpretation here, but it's 9 minus x squared minus y squared. Compute the partial derivative of the Lagrange function, so 1 minus 2 lambda x equal to 0, and with respect to y it is 2 minus 2 lambda y equal to 0. Obtain lambda from the first and second equation, and then put an equal sign between these two quantities. So you obtain that 1 over 2x is equal to 1 over y, so y is equal to 2x at the optimal solution. In order to find y and x, you have to replace 2x here, but now we have a nonlinear constraint, okay? So it is x squared plus 4x squared equal to 9. So 5x squared is equal to 9. So in principle, these necessary conditions for a maximum of this function subject to this constraint, in principle, this gives two solutions. You know, this is a system. Don't worry about lambda for the moment. Just look at the system in these two equations in x and y. This one and this one. Oh, this one, sorry, and this one. One equation is linear, the other is quadratic. So we have two solutions, okay? The degree of the system is 2. We have two solutions in general. How can we find the solutions? Of course, just find, first of all, the two solutions to this quadratic equation, which is x plus or minus 3 over square root of 5, and then corresponding to each possible value of x, we have the values of y and the values of lambda here, okay? So these are two solutions. Minus, 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 or plus, 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 respectively. Of course, what is the solution to our problems? To our problem, the representation is this one. We want to maximize this function, x plus 2y. And the level curves of these linear functions, x plus 2y equal to c, where c is a parameter, are straight lines like this. Okay? If you write these straight lines explicitly, you get y is equal to c over 2 minus 1/2 x. Okay? So c is related to the intercept. The larger is c, the outer is your straight line, okay? The larger is c, the more you move in this direction. So if you move in this direction, you increase the value of your objective function, because c, which is the value of the function, increases. Clearly, if you represent also the constraint, this is just a circle, okay, centered at the origin and with radius equal to 3. Clearly, the solution, if you think about the classical tangency interpretation, clearly the solution will be at the tangency between the constraint curve, which is this blue circle, and one of the level curves of f. But we have two tangencies here. But clearly, a maximum will happen here, will occur here, not here. Because the direction of growth of our function across the level curves is this one. And we have to maximize our function. So the tangency will be here. So when we have more than one tangency point, what is the strategy to arrive at the solution? To select one of the 2 points among 2 or 3 or maybe more. One, first consideration, the nature of the problem may exclude some solutions. For instance, if these only positive values of the variables make sense, clearly the solution will be this one and not this one. Second, look at the direction of the arrow. If you want to maximize this function, you have to look at the tangency between the constraint curve and the highest level curve. But the highest level curve is not this one, it is this one. The highest level curve compatible with the constraint is this one, okay? And there is another general result, which is this. And this is the analytical condition for optimality. So this is the second order condition for a global constraint maximum or minimum. It is very useful because in principle we should check that our results are actually a maximum, a constraint maximum or a constraint minimum. It depends on the problem. And this is the statement of this condition. Consider the problem in the one in green and the one in red are respectively a maximum and a minimum problem, okay? So maximize f of xy or minimize f of xy subject to g of xy equal to b. The point is that when you build the Lagrange function and you write down the first order conditions, these are compatible with both a maximum and a minimum. But if your problem is maximizing, we must be careful, okay? If your problem is minimizing, we must be careful. We have to prove that we actually obtain a maximum or a minimum. So consider this problem. Suppose that x star, y star is a stationary point for the Lagrangian. Stationary point means a solution to that system. A stationary point for the Lagrangian. Partial derivatives of the Lagrangian are equal to 0 for a given lambda equal to lambda star. Then pick this lambda star and put this lambda star into the Lagrangian. So replace lambda with lambda star here. We have a function of two variables with a specific value of lambda star, the parameter. If this function of two variables with a specific value of lambda star inside is concave, then x star, y star solves the maximization problem. Okay? But if Lagrange function of xy lambda star is convex instead, then your x star, y star solves the minimization problem. Okay? So basically, when we get two solutions, we have to solve the problem like this. We have two solutions here. We have one, they are simple because either all positive values or negative values, or all negative values. In the first case, we have a lambda star which is positive. If you put your positive lambda star here, plus square root of 5 over 6, anyway, it's a positive number. This quantity, regarded as a function of x and y, is it concave or convex? Linear, x plus 2y is linear. Then lambda has been replaced with a positive value, so it is positive, times, remember, x squared plus y squared is convex. Why? It is a positive definite quadratic form. So the minus this plus a constant is concave, okay? So linear, concave times a positive constant, concave, this is concave, okay? So L of x, y, lambda star, where lambda star is the positive among these two values, is a concave function. So go back to our rule. If L of x, y, lambda star is concave, then our solution solves the maximum problem. Since our problem was actually that of maximizing the function, we found the solution to our problem. If instead L of x, y, lambda star is convex, then what we get from the system solves the minimum problem. So if we go back here and we replace the negative value of lambda here, negative makes this to become convex. Convex plus linear is convex. So Lagrangian of xy lambda star, in this case, is convex. So the solution to our system corresponding to this is a minimum, okay? And it is also intuitive because if we want to minimize our function, we don't have to move in this direction. We have to move in this direction. And the optimal, let's say, optimal level curve, which is compatible with the constraint, is this one. So this is a minimum point, okay? Is that intuitive enough? We have a condition, a second order condition, which is exactly the same as for unconstrained optimization, provided that we replace in the Lagrange function the specific value of lambda that we found from the solution. Then we may have a concave function, concave Lagrangian, or a convex Lagrangian. And our reasoning is then the same as for unconstrained optimization. Concave, maximum, convex, minimum. Now this is a powerful second order condition. So, and here is the description of what my comments said before, okay? So here is the description. The two solutions And my reasoning, my line of reasoning above. So it's summarized here. This is a general example on the Cobb-Douglas, which will be part of tomorrow's class. There is another example on the Cobb-Douglas. Maybe we can solve this one. First one, and then this is a very typical problem, a constraint maximization with a Cobb-Douglas function in n variables and one linear constraint. So it's what we do here is obtaining the solution in general. Of course, then you can practice a lot with this example, because you can just, for instance, assume 3 variables, specify the exponents in some way, provided that they are positive, specify the unit coefficients here, the unit prices here, in some way, as positive quantities, and try to solve, practice and solve these problems, and then check that your solution corresponds to the general solution that we find here. So in a sense, this is also can also be regarded, it is a problem that shows some properties of the solution in the general case, not just in the 2-variable case. And it is also, you can also regard this as an engine of exercises, because you can just select some positive values and solve the corresponding exercise without knowing the general structure of the solution, and then check your result. So what is the general structure of the problem here? We want to maximize by choosing the, let's say, consumption vector x, includes the quantities to be consumed of n goods, by maximizing this function, power function in n variables. The coefficients here are positive quantities. This is called u of x, subject to a linear constraint. These are the unit prices of the n goods. These are the quantities consumed, and m is the budget in a time unit, for instance, 1 month. We build the Lagrange function. L depends on the quantities consumed of the n goods and on lambda. Lambda is a unique Lagrange multiplier for this problem, because we have only one constraint. Okay? So it is the original function plus lambda times m, the budget, minus the expenditure. The expenditure is just written here with a short notation of the sum, okay? Sum of PSXS. Okay. We exploit the structure of the partial derivatives. The derivative of the Lagrangian with respect to x1, just write this, exploit the property alpha 1 divided by x1 times capital U, where capital U is the original function, minus lambda P1, because the only term here that includes x1 is P1 x1. Same structure for the other derivatives. Alpha 2 divided by x2 times u minus lambda P2. Alpha 3 divided by x3 u minus lambda P3. Alpha n divided by xn u minus lambda Pn. So we have n conditions plus 1, which is the constraint. In fact, we have n variables here plus our parameter lambda, which also requires a numerical value here to solve the system, plus one condition. So n1 unknowns, sorry, n plus 1 unknowns, n plus 1 conditions. Now it's very easy. What we do in general, we try to obtain lambda in each equation, right? We do the same here. So if I obtain lambda here, I obtain this divided by P1. From here, I obtain this divided by P2, and so on and so forth. So lambda is equal to alpha 1 u divided by x1 P1, but from the second equation, it is equal to this. From the third equation, that would be equal to alpha 3 u divided by x3 P3. And from the last equation is this one. Now, forget about lambda for a moment. Look at all of these this chain of equalities is in fact a certain number of equations. This equal to this equal to the one that I obtained for the third term, and so on and so forth, okay? So I can write down that alpha 1 divided by x1 p1 is equal to alpha 2 divided by x2 p2, because all of these have the common factor u, which can be eliminated, okay? Clear? I have a system of these n minus 1 equations obtained by this chain of equalities and by eliminating u in each equation, plus the constraint. So it's not difficult. We can arrive at a general solution to this, because I can express here p2x2 as a function of p1x1. Instead of trying to write x2 as a function of x1, the quantity consumed at the optimal solution of the second good in terms of the quantity of the first good, just look at the expenditures. The expenditure is the quantity times the price. It is easier to solve this way. So it is the expenditure for the second good. This is the expenditure for the first good at the optimal solution. So we get p2x2 is equal to alpha 2 over alpha 1, p1x1. But from the third, from the other equation, I get p3x3 is equal to alpha 3 over alpha 2, p2x2. Now, p2x2 is this one. If you replace this blue quantity here, you can simplify alpha 2 and alpha 2 in the numerator and the denominator. And again, you have the expenditure on the third good in terms of the expenditure in the first good, okay? And all of these have a very simple structure. Just divide. So for instance, second good is alpha 2 over alpha 1 times expenditure of the first good. Third good is alpha 3 over alpha 1 times the expenditure of the first good. And the same for the nth good, okay? Now, what is the next step? All of these quantities have been expressed in terms of p1x1, which is the expenditure in the first good, but now we have this equation. So this will become an equation in p1x1, okay? p1x1 plus p2x2 plus p3x3 plus pnxn equal to n, the budget constraint, replace to p2 its expression in terms of x1, to p3 its expression in terms of x1, and so on and so forth. You get p1x1 that multiplies the sum of the coefficients. But the sum of the coefficients is just the sum of the alpha exponents divided by alpha 1. If you take the sum of the exponent, you can also call the sum of all the exponents in the Cobb-Douglas function as alpha, for instance. This is a number. And you get that p1x1 will be equal to m, the budget, times alpha 1, divided the sum of all the exponents. Okay? This one. p2x2 will be equal to m times alpha 2 divided by the sum of all the exponents. And so on and so forth. So the solution has a very simple structure. At the optimal solution, the expenditure, don't focus on the quantities. The quantities will be the next step, okay? Divide by the price, not a problem. The expenditure in each good at the optimal solution is just equal to the budget times the exponent that that good has in the Cobb-Douglas function divided by the sum of all the exponents. And since okay, so this is the expenditure. That would be the budget times this divided by the sum of all the exponents. So one may express the solution in this way in terms of expenditure shares, okay? Not how many euros is it optimal to spend in good one, but which fraction of the budget is it optimal to spend in the first good, which fraction in the second good, which fraction in the nth good, okay? It is a much more sensible way to express the solution. And here is the formula. So the expenditure in the first good divided by the available budget, which is the expenditure share on the first good, is just the exponent of the first good divided by the sum of all the exponents in the Cobb-Douglas function, okay? Which is a very simple way to express the solution, okay? And if we are interested in particular in the consumption in physical units, okay, just take the solution in terms of expenditure share, multiply it back for the budget and divide by the price, and you have the solution in terms of physical units, okay? And I also want you to look at this structure of the solution in terms of physical units. The optimal quantity to be consumed, for instance, of good one is the budget times alpha 1 over alpha. Alpha is the sum of all the exponents, divided by P1. So you see a very simple example of a demand function in economics, okay? The quantity demanded of the first good is inversely related to the price, okay? If the demand function, as usually it is stated as a function that relates the quantity demanded in terms of the price of the good, okay? And often it is just stated in terms of a function. But in general, these functions must be micro-founded. That is, they must come out from some optimization problem, okay? And this is one example. The optimal demand for good one is inversely related to the price by this function, okay? The optimal demand of good 2 is inversely related to the price of good 2, and so on and so forth. Okay? These are examples of demand functions in microeconomics. These are examples of so-called isoelastic demand functions because they have an elasticity equal basically to -1. Okay? So they are isoelastic demand functions. Because they are power functions in one variable. Okay, constant times P1 to the power of -1. Okay. We may have many more models with demand functions specified in different ways, but in many cases, these demand functions can be micro-founded, so they can come out from some utility maximization problem with a budget constraint as the optimal solution. Okay, so this is one example. I invite you to look at the next example, which is one in which I have just specified, I just assumed 3 goods, specified the exponents in this way, specified the prices in this way, and then I try to exploit the general result here and write down the solution to the problem immediately by using the solution formulas here, okay? And I get this. X star 1, X star 2, X star 3. These are the quantities, or in terms of expenditure shares. It is optimal to consume 1/3 of the budget in good 1, 2/9 of the budget in good 2, and 4/9 of the budget in good 3. But the exercise now could be for you to forget about the general formula here, build the Lagrange function, compute the partial derivatives, and solve the problem directly. That could be very useful to deal with this kind of computations, I mean, if you like. And you have to obtain the same results here. This is the solution in terms of x1, x2, and x3. Okay? So tomorrow we will see more problems, but another thing that we can do with this problem is to transform this function to keep the same constraint as above, but to transform this function with an increasing transformation. So that the objective function to be maximized is no longer this one. It is an increasing transformation of this one, And this increase in transformation means function of one variable, could be take the log of the objective function, okay? So would the solution, the optimal solution, be the same if instead of having this function to be maximized, we have an increasing transformation of this function? For instance, the log of this function, which would be log of 10, which is a number, can be neglected, plus 1/2 log of x1, plus 1/3 log of x2, plus 2/3 log of x3. The answer is yes. The optimal solution is the same, because we can modify the objective function by taking an increasing transformation of this, okay? And we obtain the same optimal solution. This is quite a general property, and this is illustrated with this example. You see, this is basically the same function where I neglect the log of 10, which is a constant. A constant doesn't affect the optimal solution. And I try to solve this. If you try to solve this, you work out a first order condition, you get exactly the same solution as before. It's even easier. Working with the log transformation of a Cobb-Douglas function is even easier than working directly with the Cobb-Douglas function, okay? So I invite you to look at these examples, because they are all constructed in a way that you can double check your results. This is the general proof that this works. You can maybe see it tomorrow. And then tomorrow we'll show you this example, which is the example which is called the quasi-linear objective function. And tomorrow I will show you also basically 3 or 4 or 5 more summary exercises on the first part of the course. Basically, there is nothing new tomorrow. There is just the remaining examples in this set of slides, which are exercises. They are all exercises, plus one additional set of slides of summary exercises on basically partial derivatives, partial elasticities, unconstrained optimization, constrained optimization, which is the core of the criteria of the first, for the partial exam, for the midterm exam. I think we can maybe stop here today. So let me see. Just one more thing. So I suppose I already uploaded also the slides for tomorrow's class. But anyway, there will be, I will show you an exercise on the computation of partial derivatives and elasticities of a multiplicative model, linear approximation of a two-variable function. As explained, I will not ask you to compute second-order approximations, just linear approximations. Another exercise on unconstrained maximization, and a very similar one left to you as an exercise, which is similar to the previous. Problems of constrained maximum, with one way in which we can also use the second order condition. Sensitivity analysis. So there is nothing new, basically. Nothing new, only exercises. Chain rules, time derivatives, and time growth rates. And again, unconstrained maximization. Okay, so basically there is nothing new. And a minimum problem, maybe. A strictly related minimum problem. So I will show you maybe a minimum problem, and then I will leave you as an exercise to solve a related maximum problem, okay? So only exercises tomorrow on the most important parts of the program. Okay, I think we can stop here. Okay, see you tomorrow. Let me see if there are questions. Could you explain the examination method at the end of the lesson? Our examination method is, I explained this, I remember, in the first class. There will be, I also, maybe I can upload, I've shown the way that the exam paper looks like in the first class. I can maybe upload them to the Virtuale, but basically there will be one exercise in which you will be required to provide the full solution steps and a number of short exercises, typically computation of derivatives, computation of elasticities, simple linear approximation and things like this, in which you are only asked to provide the final result. Okay? So.
I think she was asking about the setup that we have to organize.
This will be online examination, so there will be, okay, so there will be an online examination using Zoom, a Zoom platform, okay? And the problem here is that there are some students who couldn't enroll, but I would like to admit all of them also to the partial, the midterm examination, provided that I have a mailing list for these students, because I will then create an additional account for Zoom and open 2 different exam sessions, because I cannot use the Alma Esami for that. So the point with the Alma Esami platform is that only students that are have regularly enrolled can participate to the exam, can attend the exam. But I would like to admit to the examination also students who will be presumably enrolled in the next month or so. But in order to do that, I need an email, a mailing list for those students. So this is just to tell you that if you are able to provide me with an email and a mailing list for these students, I can then extend the examination to all of them. But if I don't have a mailing list, it's very difficult, because I must provide a setup which is fair. So, for instance, both examinations with the Zoom platform, not one with the Zoom and the other one with Teams, for instance. So I need a mailing list for the students who haven't concluded the enrollment yet. But maybe I will put also an announcement in the Virtuale over the next days. Is there anyone here in this condition? Okay, students at home, online students, if you can provide me with if there is anyone who wants to be in charge of providing me with a mailing list of all the students who would like to participate to the midterm exam, even if they haven't concluded their enrollment yet, I would be very thankful. Because I cannot accept last-minute students. This is the point, because I don't know how to admit them to the room. Any comments from you? Yes, you have to solve it on a paper, and then you have to take a snapshot. I will upload also the instructions for the online examination, which is they are ready already, because it's the same as last year. You have to write this on a sheet of paper, then you have to take a snapshot. You will be allowed, let's say, 10 to 15 minutes to take the snapshot, to upload it maybe to your computer, and then to upload it to the Esami online platform. Okay? So maybe you don't know how online examinations work. You still don't know. Okay, let me spend 2 minutes. Okay? There is a okay, listen well, all the students at home, because I'm going to spend a couple of minutes to explain the online examinations with Zoom, but please consider that all of these are also in the UNIBO website. Okay, so the instructions for students, general instructions for students are there. I will upload specific instructions for this exam, but it works like this. First of all, if possible, you have to register to the Alma Esami. Okay, if possible. Otherwise, there is a second possible way for students not yet enrolled. Second, there will be, you can access the online examination using the Alma Esami, okay? So there will be virtual room or virtual examination just to be admitted into the room. Okay, but this is in combination with another platform which is called Esami Online. You don't have to combine anything, it's already combined, the two, okay? When you access through the Alma Esami, you can also access through the Esami Online platform, through both, it's equivalent. You will be at the same time in the room, and you will have access to the PDF file of the exam text of the exam paper, okay? To the PDF file. Then you can look at the PDF file, download it on your computer. I will have the control of your screen. So you must share your screen. This is the reason why I use Zoom instead of Teams. You must share your screen, and then this must be shared. This must be pointed to your PDF file of the text and nothing, and not the Desmos, for instance. And you have to solve the exercise and write the solution on a sheet of paper. Then at the end, you will be allowed, let's say 15 minutes to take a snapshot, upload a PDF file, and upload the PDF file to the Esami Online platform. There will be a kind of area where you can drag and drop, is that the true word? Drag and drop, move your file on that area, and this will be automatically uploaded to the Esami Online, and you will have a confirmation of this. You will see a kind of green area, oh, thank you, your exam has been delivered, okay? And nothing more. I mean, it's very easy. You will be allowed something like 1 hour. It depends on the type of exam, but 1 hour and a half, 1 hour and 40 minutes, plus the additional time required to take the snapshot.
We have to take the snapshot.
Yeah, with your mobile. So you can, of course, you cannot use your mobile for the whole duration of the examination, but only for the final 10 minutes, let's say. You are allowed to use your mobile or your tablet, take a snapshot, and if you can do that, just upload the file to the Esami Online from your mobile directly. If you cannot do that, just move your file to the computer and then upload it from your PC.
Would it be possible to do the exam here? Because I have bad connection at home.
Okay, I see the point. I mean, I don't know how to organize this. I mean, I think it is possible in principle, but you should. I can just let the head of the course know that some students would. I mean, they would like. The point is that if you don't have, I mean, I cannot group some of you in this room because otherwise, I would need a person here in the room. Yeah, so. I don't know how to fix this. I don't know how to fix this because the examinations are, if the examinations are online, everybody is responsible for his
Yeah, but the fact is, if we must share our screen and at the same time share our face and use internet, we need a lot of bandwidth. Speaking about the
look, it is already the third year I'm doing this, and I never had a big problem in the sense that students were asked to withdraw from the examination because they disappear for a long time, so it never happened to me. It never happened. It may happen that I mean, that's true. I never found a situation in which students disappear because of bad network quality, or maybe for a few seconds. But in that case, if it is only for a few seconds, in that case you can be admitted again to the room.
But wouldn't it be possible to just reserve a room here? And I mean, if we're online on Zoom with cameras and audio on, then that's kind of a control that we can't talk with each other even though we're in the same room.
Okay, I don't know how to fix this. I mean, I can just talk about this to the head of the course to see whether this is a common issue, a common problem, at least for these first year examinations. But I don't really know how to fix it, because in principle, if there is a room with more students, I would need a person being here to control the functioning of everything, which doesn't seem possible. I mean, at the moment, at least at the moment. I don't know. I will see what's possible, but in general, this has worked well with any students, all students at home. I mean, any student at home, or in a private room, or okay. Anyway, I will let you know. What's possible. The point is that I cannot. The exam cannot be at the same time. At least to me, cannot be at the same time in presence and online. I mean, also students in a room, in principle, should be online, because in presence plus online is a big problem. Is a big problem, not only for me but for all colleagues of mine. Okay.
Maybe Anna knows how to arrange this, because she proposed us this kind of method.
Oh, you proposed this already to Anna Montini, so maybe there is a way to fix it. Okay, that's. I mean, your point is, if I want a person to help me with the examination, I can do that at home and also in the room, right? So this is your point, if I understand that. And so why not being in the room? Okay, let me talk about this with Anna Montini, but please be aware that I'm not sure about the answer and about my decision. Okay. I think that's all for today.
Thank you.
Bye. Okay, bye. Oh, one question on the clock. Very good.